Hi, this is my video number 7. My video number 7. In the last video, I'll talk on the bounded sequence. Yeah, we have a bounded sequence. I've given the appropriate example, bounded sequence. So what is the bounded sequence? If you can find m positive, such that the terms of the sequence less than m for all n. For all n. So in this case, we say the sequence un is bounded. Yeah. On the other hand, for the unbounded sequence, if you can find a number m positive such that the absolute of un is greater than or equal to m for all n. So in this case, we say m and un is unbounded. Yeah, in this case, we say un is unbounded sequence. A simple example for this I can look at is like if you have a sequence like 2 to the n. Alright, so if you take the absolute of those un, and this is always positive, so we have this is 2 over n, and obviously for all n, the n equal to 1, 2, 3 and so on, this is equal to greater than or equal to 2, which is our m. So in this case, for all n 1, 2, 3 and so on. So in this case, we say this is unbounded sequence. Alright, so I have explained to you what is the sequence, how to write a sequence, and as well as the main problem that we are looking in the sequence, which is bounded, unbounded, increasing, decreasing, converge and diverge sequence. Now for this lecture, I would like to give a general formula how to get or how to find the general formula for a sequence. A general formula for a sequence. So we know that a sequence can be defined as a function whose domain is the set of positive integer. Yeah, we have our domain is a set of positive integer. For example, if you have of fn un 1 over 2n plus 3 for n equal to 1, 2 and so on. So you can write this as a sequence un as if you list down all those things, you have 1 over 5, 1 over 7, 1 over 9 and so on. So we, of course, as we mentioned earlier, instead of fn we write a un, yeah, as a function. Now let's just look at the couple of example of how to get the general formula, because there is no specific specific way of doing it, except from if you can just look into it, then and then the rest is how do you get the general terms. Yeah. Now let's look at this example. Let's say if I have 1, 4, 7, 10, and so on. Alright, UN, and so on. So the purpose now is to find what is UN. What is UN? Yeah. If you look at the general formula that we, the element of that sequence, we have 4. So we notice that there is increased 3 each of them. All right, and then so from there you can have like UN give as a, you have a 1 plus n minus 1 times by 3. Alright, so but basically this is the arithmetic sequence. Then you can write this as a, you can solve this, this is 3n minus 2. So that's the general formula that we have for the UN. Okay, and other example, if you have, let's say this number 1 and number 2, we consider this sequence 1, 3, 9, 27, 81, and so on. UN that. As you can see here, this is 3 to the power of 1, 3 to the power of 2, power 3, alright, but this is 1. So which means to get 1, this is 3 to the power of 0 here. This is 3 power of 1, this is 3 power of 2, this is 3 power of 3, and so on. So but we don't, in sequence we don't begin with 0. So what we can do is just like 3, 0 is 1 minus 1, you can see. Alright, that one 3, 2 minus 1, that one 3 minus 1. Then you can find this by inspection. Then you can see that this is actually 3. If you consider this first term as your n, then it gives you n minus 1. So this is your sequence. I mean your n terms. Okay. Right. Other example, of course there are many form of sequence. One of them is this is a normal, where you can find n terms straight away, but in other case, for example this one, you have square root 2, 1 over square root 2, 1 over square root 4, 1 over square root 4, 1 over square root 8, 1 over square root 8, and so on. Yeah, so we have 2, 4, 8, and so on, which is 2 to the power of n, yeah, inside here, 2 to the power of n. So how to obtain the sequence like this to get the UN? UN. So we want to find UN. So what I can suggest is that just look at where the sequence start changing. So for example, in this case, we have this between term 1 and term 2, they don't change. This sequence doesn't change. And then, but when it goes to 3, then it's changed. Then same 4 doesn't change, and 5th, and so on. So you can see this sequence start changing there. And we should expect the same pattern like that. And as well as this. So what you can see, this is the odd terms. 1, okay, first, third, 5th, and so on. And then second, 4th, and so on. Alright, so this is the even terms, this is the odd terms. So of course, to find the even and odd term, even and odd, we have for even 2 times n, for odd either 2n minus 1 or 2n plus 1, it depends. Okay, so for this case, of course the general part is we have 1 over z, and then inside there, so we have, this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. So basically we have 2 to the power of n. But this is for the first term. Then this is, we can say, first, third, fifth, and so on. So we have 2n minus 1. Okay, and then for even terms, we can have, basically they are similar, so the formula we should expect the same. So u2n, this give you 1 over z 2n. So this give you the n terms of that sequence. Okay, let's look at other example. Yeah, give you a couple of example. We have 3, 4. Then look at this example. We have minus 1, 1 over 4, minus 1 over 9, 1 over 16, and so on. Okay, and then un, and so on. Again, the purpose is to find the n terms of that sequence. Now, if you look at here, we can see this is 2 to the 2, right? This is 3 to the 2. This is 4 to the 2. All right. So we should expect for the n here, we have n to the 2. But the problem now, we have this plus minus here. This one minus, this one plus, this one minus, then plus again. Then we should expect next is minus, then plus, then minus, then plus. Now to obtain those alternate sign of the sequence, we use the negative 1. But to the power of what depend on this, when n equal to 1, because this is the first term. When n equal to 1, yeah, first term, which means our n equal to 1. For terms, first term, n equal to 1, so we have negative. So which means we have to get the negative here, yeah, to stay negative. So we have this to the power of 1 for the first term. For the second term, we have minus 1 to the, because this is positive, so we need even power. And then for the third, we need again odd power. So what we can say from there, because this is the third term, automatically give you the odd power. So therefore, our un is given as, so we have minus 1 to the n. Alright, so because this is power 3, minus 1 to 3, you got negative. This is power 4, you got positive. This is power 5, negative, and so on. And then the denominator, we have the general term is n squared. So therefore, that's your n terms. That's not really hard actually. Next example, let's say we have a sequence of like 1, 1, minus 1. We have 2, 2 minus 2, 3, 3 minus 3, and so on. Then you have un here, and so on. Okay. We know that this is our u1, this is our u2, this is our u3. For the repetition of terms like this, as we discussed earlier in example number 3, in this example here, we look where the change starts. If you look at here, they really change here 1 to 4. All right, and then 2 to that terms. So this is term number 3, term number 4, U4, this is U5, this is U6, then we have U7 here. And the same thing for the second terms. The second terms, that goes to U5, that goes to U8. U8. And so in this case we need 3 basically, and the other one we just change, we just have a negative there. Okay, so to have this 1, right, 1, next is 4, next is 7, next we should expect 11, alright, next we should expect 15, and so on. So we have U, how to get those things, 1, 4, so 3n minus 2, is that correct? 1, you got 1, when n equal to 2, 6 minus 2, you got 4, when n equal to 3, 9 minus 2, you got 7, so it seems correct. And the terms is that, the element is that we have, this is 1, which is n, this is just n, so this is just equal to n. For the U2, U4, so you have U 3n minus 1. This is also n, and then you have U 3n, this gives you minus of n. That's for n. 1, 2, 3, 4, and stress. Okay, so that's the general formula to find the n terms. Yeah. Others you can, you just think that way. Of course, we have some more example there. What about this example here? If you have 3 over 5 minus 4 over 5, 5 over 1 to 5 minus 6 over 6 to 5, and so on. So that gives you our un is, you look at this, the upper part here, to get 3, this is the first term, so we have 1 plus 2, right? 1 plus 2, 2 plus 2, 3 plus 2, and so on. Yeah. So we have, let me write here, 1 plus 2, this is 2 plus 2, this is 3 plus 2, and we should expect 4 plus 2. So this part here, it seems you just add up the same number, 2 plus 2 plus 2. The change is here, 1, 1, that's okay, 1, 2, 3, 4. So just that's mean n. So means the numerator is just n plus 2. What about the numerator, the denominator here? You have when n equal to 1, so basically this is 5 to power 1. This is this should be 25. Yeah, this should be 25. Okay, so we have 5 power 2, this is 5 power 3, and so on. So we should expect this basically over 5 to power n, 5 1, 5 2, 5 3. Okay, so we have 5 to power n, and we have those negative alternately. Yeah, positive, negative, positive, negative. So the odd terms is positive, the even term is negative. So we have a minus 1 to get the odd terms. You just put n minus 1, so you can have those sequence. Okay, what about the sequence we define recursively, like Fibonacci sequence, like Lucas sequence? We have many kind of those kind sequence. let's look at those examples. If you have a sequence like we have 1 1 2 3 5 8 13 and so on, you have un. So this we call it as a Fibonacci sequence. Yeah, Fibonacci sequence. So how to find this? So look carefully. Okay, look carefully. So the first term is look like the first term, and the second term is just a fixed number. Yeah? So you can say u1 is equal to 1, u2 is equal to 1. But for the u3 here, you need to add up these two to get 2. For 3, you need to add up these two previous terms to get that 3, as well as 5, as well as 8, and so on. So which means we have un plus 1, this is equal to un plus un minus 1. For n equal to, you can see from here, n equal to 2, you got so for n equal to 3, 2, 3, 4, and so on. Alright? So this is the Fibonacci sequence. We can find up to n terms. And what about this sequence? Another example I give you here. What number is this? 6, 7, 8. If you have like 1, 3, 4, 7, 11, 18, and so on. un. Okay, this is known as Lucas sequence. So how to find this? So for the first two terms here, this is fixed. So I can say this is u1 equal to 1, u2 equal to 3. Whereas for third terms, we need to add up two previous terms, term 1 and term 2. And for fourth terms, you need to add up third terms and second terms. So what we have here is un is equal to I can say un minus 1 plus un minus 2. Yeah, for n greater than what? I can say n 3, 4, 5, and so on. So this is our n terms given as not just n, but n terms here we have. Yeah, from there, from this recursive relation, we call it recursive relation. Recursive relation. Yeah, same with this, and same with the Fibonacci sequence. Okay, so that's the for the general formula of the sequence. Yeah. Now I want to discuss on the limit of a sequence. Limit of a sequence. So first thing, what is the limit of the sequence? If it plots, or I give you an example of one sequence. Let's say I have a sequence like this. That sequence. Okay, and so on. So it is obvious that in this case, this sequence will not exceed some numbers, let's say somewhere here. That. So let's call this number m. Okay, so for this sequence, so each of the element in that sequence does not exceed the number m. So in this case, we say that this number here as a limit to that sequence. Yeah, maximum that those element of the sequence can have. Or we can have this is for the case of increasing sequence. What about for the decreasing sequence? The same thing for the decreasing sequence. So let's say I have sequence like this. So you can see for both of these example, the sequence converge to its limit. Yeah, sequence converge to its limit. Sequence converge to its limit. Now comes the definition of the limit. Yeah. So from there, I hope you can have an idea of the when we say the limit of the sequence first thing, then the other thing is the convergence itself. Yeah, sequence converge. Now, if you consider, for example, if you consider the I give you the specific example. Let's say if we have un is equal to n over n plus 1. Yeah, this is a increasing sequence and bounded. Increasing sequence and bounded. So what we have here? So we have this is 1 over 2, 1 over 3, and 1 over 4. 2, 3, 3 over 4, 4 over 5. Okay, so it's 10 to 1. You can see here in this case, yeah, from half, this is greater than half and it's close to 1, and you have later on very close to 1. So basically let's say half is here, let's say 1 is here, so you have that kind of sequence. So it not increase or it not exceed n. Okay, so you can see from this example, this is just a sketch, to give you the idea what is the limit, what is the convergence. This is more specific example we have. So from these three cases, if I would say three cases here, yeah, whereas for the number 1 and number 3 here, they are just a similar pattern. As n increase, I can say as n increase, okay, the sequence un converge to its limits. Let's say those limit L. So let me write this in word. So as n increases, un approaches its limit. Okay, I hope you can understand those things. As n increases, as you can see here, this is because this is n, yeah, n increase from 1 to, when we increase n, the sequence here approaches its limit here. It will not increase, it's not exceed 1 in this case, but getting close and close and close and close and close to 1, and very close to 1 in fact, when bigger n we choose. Okay, now so all this thing, yeah, I would say that we can write this thing, the limit, yeah, the limit of n goes to infinity, when n goes to infinity of un, I give you the formal definition later on. This is equal to, or I would say approach its limits. For example, in this case here, the limit as n goes to infinity, we have n over n plus 1, this is equal to 1. Yeah? This example here, represented by this sketch, as you can see, it approaches its limit. Generally, we have this. Okay, now what's the formal definition of this? So we have definition. So a sequence un has the limit L, and we write as limit of un n goes to infinity, this equal to L. The definition if and only if and only if, normally I just use if with double F, yeah, for every epsilon positive, we can find, or there exists integer n positive, yeah, such that we have un minus L less than epsilon for all n greater than n. Okay, so let me write this in short. So we have, let me write this in form. This is just a rewrite of those in Word. Alright, so we have limit of un n goes to infinity. This is equal to L if and only if, okay, for every epsilon positive, we can find n positive such that un minus L less than epsilon for all n greater than, yeah, small n greater than capital N. So you need to know this sequence, that definition. So let me explain in a bit more detail what do we mean by that definition. What is the epsilon in this case? What is n? Alright, and what does that symbol means? Alright, so probably the easiest way to explain this, let me sketch. Let's say I have a convergence sequence, a sequence with limits. So let's say I have this sequence. Okay. So as we can see, this is the n. All right, and this is our un. And what is L? L is the limit of that sequence, which means our L is indeed exists. L is in that exists. So I can say L is the limit. So in this case, our limit is where the maximum or the biggest if it increase, the smallest if it decrease. Now in this case, the sequence is increased. So I put the, let's say, the bound or the limit, let's say that I have. Okay, let's say I call this as a L. So automatically you can understand that this symbol here the modulus of un minus L, which means the distance between the n terms and the limit itself. Yeah, the distance between the n terms and the limit itself. What is the n terms? The n term is here. So we have here, this is u1. Oh, just a minute. My pen jumping all over. All right. So we have u2 here. This is u1. You have u2. We have u3, and so on. So this is our un. There's our un. So if you consider u1, take the difference u1 minus L. Of course, this gives you a positive number, but look at the difference. Here un, u1, 1 is here, u1 is here. This is not u1, sorry again. This is 1, 2, 3, and so on. So this is u1, this is u2 here, and so on. Okay, that's correct. Now, you can see u1 minus L, u1 minus L. This is u1, this is u, this is your L. So definitely from there, this is bigger than u2 minus L. Correct? un minus 2 smaller than that, or that one is bigger than that. So what I want to say is that this is always like that. u3 minus L, u4 minus L, and so on. So as we can see here, this term here getting smaller and getting smaller and getting smaller. The more to the right you go, the smaller its numbers. Alright? And then you can increase this, you can increase those things up to the general terms. We have un minus L. Basically, it gives you some numbers here. un minus L give you some numbers, pretty big. Alright? And then a little bit smaller, un minus 2 still give a numbers. And this one much smaller compared to the previous one, and still some numbers, and some numbers smaller than the previous one. So we should expect that for the n terms have still have a distance, because it's not 0, because un is always not different than L, but it gives a small number. Those small number we call it as an epsilon. So this is a positive number, always positive, but not big, So those small number, we call it as an epsilon. So which means the difference between the n terms very close enough to L. Let's say somewhere here. Let's say un, my un is here. This is un. You take the difference here. That difference gives you epsilon. Okay, so for this un, we can have a number n somewhere here. This is our n. And you can see, look at from the definition, compare with this. Look at the definition we have for n greater than n. So n greater than n means this side here. So here we have n plus 1, we have n plus 2, and so on. So what happens if we increase n greater than that n? What happens is that our sequence here, the terms that always less than that epsilon. Yeah, always less than that epsilon. So that means those definition. So I hope you can understand those things. Okay, so let me repeat that. What is epsilon? Epsilon is actually the distance between un and the limit itself, L, and n is some numbers that satisfy those conditions un minus L less than epsilon. So we need to find those things. So we have a result based on all those things you can see for the limit axis. And if you look at for the divergence sequence like that, in this case we don't have a limit, because the bigger the n, the bigger the sequence. You can see here as n increase, un also increase. this sequence doesn't converge to a specific value. Example, of course, you can think of like 2 to the power of n. I think just take a simple example, or obvious example. So if you consider this, you can see that the bigger the n that we choose, and then un getting bigger and bigger. So in this case, the sequence doesn't converge. And as we have shown in the earlier of this video, that this kind of sequence is a divergent sequence, or we say unbounded sequence. Unbounded sequence or divergent sequence. Now we have a spontaneous result, I would say, if the limit of the sequence n tend to infinity un exists, then we say the sequence un, the sequence converge to its limits, or just converge, yeah, just converge, or is convergence, or we can say this sequence is convergent. If this is not the case, the sequence diverge. So you have two things here. The first thing is that the existence of the limits. The existence of limit is that we can find the limit. You can find those L. Yeah, we can find those L, so that the limit exists. So if not, then the sequence diverge. Okay, so symbolically or mathematically, this is the notation that we use. You have to remember this for the limit of the sequence. Alright, limit the sequence, we say limit un, n goes to infinity equal to L, if and only if for every epsilon positive, we can find some positive number n such that it satisfies that condition. Yeah, the distance between un and L less than that number epsilon. I wanted to give you example. I have a couple of example here. So, okay, in this video, let me give you one example. Okay, and then next, I think because it's almost an hour now, I give you in the next lecture. Just stress more on the sequence itself and the definition. All right, because this part is quite important for you to understand further. So now let's consider this example. Okay, we show that the limit 1 over n goes to infinity, this equal to 0, or prove that, I would say. Show that n goes to, so of course if you look at here, if you put epsilon there, if you put infinity there, then it's equal to 0. But how to show that, how to prove that? Okay, so let's come back to our definition. I write again. The definition is, we have the limit n goes to infinity un is equal to L if and only if for every epsilon positive you can find n positive such that un minus L less than epsilon for all n. So that's the definition. So we're going to use this definition to show that, or to prove that, the limit of 1 over n is actually goes to 0. So in order to prove this, what we want to find, actually, we want to find this n. So that's what we are looking for. Yeah, can we find those n? That's the point. Now, so let's do it. So let's say given any epsilon, this is the first step that you need to have. Given any epsilon positive, then we need to have this condition here. Okay, we need to have this condition here. So from there we have un minus L, so our un is 1 over n, minus L, our L is 0, minus 0, that gives you 1 over n. And since this part is always positive, we know that this is equal to 1 over n. So what choice of n here? So remember, what we want is that this part here less than epsilon. Okay, we want this part here is less than epsilon. How to get that less than epsilon? So in order to have this, you can write that, basically just cross that around, so we have 1 over epsilon is greater than n. Okay, this is not part of the solution, but just to show you how to find those n. Okay, so we have all n greater than 1 over epsilon. So you can choose this as your n. Okay, sorry, not this one, you can choose this as your n, capital N. So you can see that if you choose anything n greater than this n plus 1 and capital N plus 1, n plus 1, n plus 2, and so on, we always have is greater than, satisfy those conditions. So therefore, from there we choose n equal to 1 over epsilon. So what we have now, because of that choice, we have 1 over n minus 0. This is, we can show from here that this is 1 over n and this is less than epsilon for all n greater n. So this is your solution. Just 1, 2, 3 steps. The important part is that how to choose n. I've explained to you. This part you just copy basically from the definition, but the choice of n here is very important. And how to get this n is how do you simplify from that. The example here is quite simple, so it's not a big deal for you to choose those things. Now again, visually, how do we get this thing? Now look at the example. From this particular example, I will consider sub-example or the subsequent of that. If you choose, for example, epsilon as a 0.001. If you choose this epsilon 0.01, because epsilon is a small number, positive, then what happened from there? Our n is basically 1 over 0.001, which is 1,000, right? 1,000. Now, if you choose any n greater than our n, which is 1,000, so let's say, for example, let's say we have choose n equal to 1001 or 1100 or even bigger, 2,000 and even bigger, and so on. So what you can see is that 1 over n with this particular n, you can check using your calculator that this always less than 0.001. Okay, take your calculator, 1 over 1001, you got what? 1 over 1100, 1 over 2000, and so on. You will find that that number here always less than 0.001. Okay, so I'll give you another example on this thing, how to find the capital N in the next example, in the next video, because I don't think I can proceed. This is already an hour. So let me conclude in the few minutes or few seconds that what we have done in this video. That first thing I discussed on the how to find Now the first thing is about the unbounded sequence. Yeah, we begin with the refresh what we have done in the previous video on the bounded sequence, then unbounded sequence, then how to find the general n terms of the given sequence, and then I start more on definition on what is the limit of the sequence. Alright, then I give a formal definition of the limit of the sequence, and then we also have the sequence if the limit exists, means the sequence converge, and I end up with example of how to use the definition of the limit of the sequence. Alright, so with that I stop here for this video. See you in the next video. Bye bye.